Hello and welcome to Sleepy Science. I'm glad you're here. Perhaps you had a long day, or maybe you enjoy falling asleep to cosmic wonders instead of counting sheep. Either way, tonight's journey is for you. Your only task is to rest. Let your mind unwind, your breathing deepen, and your body soften as if gravity eased its hold. Tonight, we aren't just looking at stars, we're drifting through our home, the Milky Way, a vast, ancient spiral of stars, dust, and dark matter, over 13 billion years old. Yet beneath its beauty lie secrets, rogue stars, invisible forces, and ancient relics that challenge our understanding. We'll travel gently from its spiral arms to its hidden core, from colossal mergers to stars older than the galaxy itself. You'll hear of black holes, stellar nurseries, and the unfinished story of a galaxy still evolving. What you hear may surprise you or spark curiosity as you drift toward sleep. Before we start, if these calm explorations help you unwind or offer a quiet end to your day, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. The Milky Way has already merged with other galaxies, and it will again. Our galaxy may seem stable, but it is built from the wreckage of others. Over billions of years, it has absorbed smaller galaxies, drawing them in, tearing them apart, and scattering their stars into tidal streams. One such galaxy, the Sagittarius dwarf, is being pulled apart now, and far off, Andromeda drifts slowly closer. In about 4.5 billion years, the two great spirals will merge. Stars will rarely collide, but their shapes will change forever, folding into a new, vast form. Even galaxies are not eternal. They evolve, collide, and begin anew. Some stars in the Milky Way are older than the Milky Way itself. Not every star here was born here. Some ancient metal-poor stars in the halo, moving in long, tilted orbits, appear to have formed before the Milky Way took full shape. They likely originated in smaller primordial galaxies that merged with ours long ago. Their chemical signatures show almost no heavy elements, suggesting they were born shortly after the Big Bang. They drift slowly high above the galactic plane, like elders from a time before spirals, before order. In their light, we see a younger, wilder universe. Our solar system orbits the galactic center at over 828,000 kilometers per hour. That's more than 230 kilometers every second. Yet it takes about 225 million years to complete one loop, a galactic year. Since the solar system formed, we've circled the galaxy only about 20 times. When the first dinosaurs appeared, we were in a different part of the galaxy entirely. The stars we see today weren't always nearby and won't always remain. Everything is in motion, quietly, slowly, endlessly. Even as we sleep, Earth turns, the moon circles, and our solar system sweeps onward through a galaxy in motion.
The galaxy is still growing. Although ancient, the Milky Way isn't finished. It continues to gather material, gas from intergalactic space, stars from captured dwarf galaxies, and streams of dark matter feeding its halo. It grows not like a living thing, but like a gravitational structure deepening over time. Some growth happens quietly. Other times, it comes with disruption as satellite galaxies are torn apart. The galaxy you live in today is not the one the dinosaurs saw. The one your distant descendants may know could be larger still, stitched from the ruins of countless smaller worlds. We don't know how many arms the Milky Way has. It seems like something we should know, but from our position inside the disk, it's hard to see the whole structure. Dust clouds obscure distant regions, stars blur together. For decades, astronomers believed there were 4 major spiral arms. Recent observations suggest maybe fewer, or that the arms twist and split in complex ways. Some fade into fragments, others wrap unexpectedly. The Milky Way may not be a neat pinwheel, but a living, layered swirl shaped by forces we still don't fully understand. Rogue stars are flung from the core. Most stars drift calmly, but a rare few are ejected at astonishing speeds, fast enough to escape the galaxy entirely. These are hypervelocity stars. Some are remnants of binary systems disrupted by the supermassive black hole at the galactic center. One star falls in, the other is slingshotted outward, hurled into the dark at over 1,000,000 kilometers per hour. These rogues travel alone, far from the galactic plane, like glowing comets with no return. They remind us that even in a gravity-bound galaxy, there are moments of violent release. The Milky Way and Andromeda are on a collision course. The Andromeda Galaxy, a faint blur to the naked eye, lies over 2 million light-years away but is moving steadily toward us. In about 4.5 billion years, the two galaxies will collide. Stars are too far apart to crash, but their gravity will warp both galaxies into long, stretching arcs. Tidal tails will curl outward, black holes may spiral together. After billions of years, they will merge into a single, larger system. A slow, elegant dance, the future of our home written across the stars. Some stars orbit backward. Most stars in the Milky Way orbit in the same general direction, but not all. Some, especially in the outer halo, move in retrograde, orbiting opposite to the galaxy's main rotation. These stars likely arrived from elsewhere, born in dwarf galaxies later absorbed. Their reversed motion is a quiet signature of their foreign origin, as if the galaxy carries old memories in its motion, stories of ancient mergers preserved in the slow turning of stars against the stream. The Milky Way may have eaten dozens of dwarf galaxies. Over billions of years, it has consumed small galactic companions, caught in its gravity and slowly dismantled. Their stars are now part of our halo, disk, or stellar streams. Astronomers have identified several of these mergers by analyzing stellar motion and composition. One large event, the Gaia-Enceladus merger, added many stars and may have reshaped the galaxy's early structure. The Milky Way is not a pristine spiral, but a composite stitched from the remains of many smaller worlds. The chemical makeup of stars reveals their origin. Every star carries a unique chemical fingerprint, a pattern of elements imprinted at birth. By studying these signatures, astronomers trace stellar histories. Some stars are rich in heavy elements like iron, suggesting they formed in dense, metal-rich regions. Others are nearly pure hydrogen and helium, born when the universe was young. These differences let scientists group stars into families, uncover ancient mergers, and reconstruct the hidden story of the Milky Way's formation. Chemistry becomes a time machine, reading a star's past like poetry written in light. The sky is full of stellar streams from shredded galaxies. Across the sky, thin ribbons of stars stretch in arcs and curves, stellar streams, remnants of smaller galaxies pulled apart by the Milky Way's gravity. As they orbit, their stars are smeared by tidal forces into long, delicate trails. Some wrap around the galaxy like ghostly halos. Others dive toward the core. These streams are evidence of past collisions, quiet mergers that built the Milky Way over eons. The galaxy, like a tree, carries the rings of its past in every thread of light. The Milky Way is warped. Our galaxy doesn't lie flat. Its disk bends upward on one side and downward on the other, forming a graceful wave. This subtle warp, revealed by radio telescopes mapping hydrogen gas, may be caused by satellite galaxies tugging at its edges or by clumps of dark matter. Like ripples in a spinning sheet, the warp shows that galaxies are never fully still. Over time, they bend, flex, and change in response to invisible forces. From a distance, the Milky Way might look like it's dancing slowly through space. You can only see about 0.00003% of the Milky Way with the naked eye. Under a dark sky, you might see a few thousand stars, an ocean of light to our eyes, but barely a droplet. The galaxy contains over 100 billion stars. Most are hidden, behind dust, too faint, or too far away. The pale streak crossing the sky is just the innermost whisper of the whole. We live surrounded by a colossal river of starlight, yet almost all of it remains invisible, too vast to grasp from within. Stars orbit the galaxy at different speeds. Unlike planets in a solar system, stars in the Milky Way move with more freedom. Some race ahead in inner regions, others drift slowly in the outskirts. This speed difference is why spiral arms form. They're not solid structures, but density waves, like slow traffic jams of stars and gas. As these waves pass, they trigger new star formation, lighting up the arms in curls of blue and white. Our sun is part of this swirl, moving in and out of these patterns across time. The galaxy is not a clock, but a current, and we are drifting in it. The galaxy holds together because of something we cannot see. By all logic, the Milky Way should not exist. The outer edges spin too fast, they should be flung into space, yet they remain. The answer is dark matter. This mysterious substance doesn't shine or emit light, but it exerts gravity, outweighing all visible matter many times over. We don't know what dark matter is, but without it, the Milky Way would fly apart. It is the invisible scaffolding holding everything in place. There's a supermassive black hole at the core. At the center of the Milky Way lies Sagittarius A*, a black hole over 4 million times the Sun's mass, yet smaller than Mercury's orbit. We can't see it directly, but we've watched nearby stars whip around it at tremendous speeds. Sometimes gas and dust fall inward, flaring with X-rays as they spiral toward the event horizon. For now, Sagittarius A sleeps, but long ago it may have burned like a quasar, lighting the galaxy from within. It is the silent conductor of the Milky Way's heart. The Milky Way has a peanut-shaped bulge. The galaxy's central bulge is not a smooth ball, but a three-dimensional peanut shape. Seen from the side, it swells in the middle and narrows at the ends, like a twisting hourglass of stars. This likely formed from the galaxy's central bar, a dense stripe of stars that rotate slowly, buckling upward over time. These inner structures are sculpted by gravity and billions of years of motion. We live in a spiral galaxy, but its heart is complex, not flat or clean, but intricate and alive. Stellar nurseries shape the spiral arms. The Milky Way's arms are woven from star birthplaces. Giant clouds of hydrogen and dust drift through the galaxy. When compressed in spiral arms, they ignite with newborn suns. These stellar nurseries are chaotic, glowing regions. Ultraviolet light from new stars paints the arms with radiant blues and silvers, tracing the spiral shape with quiet fire. Every star, even our sun, was born in one of these cloudy cradles long ago. The Milky Way is surrounded by a vast halo. Beyond the spiral disk lies a spherical halo of ancient stars, globular clusters, and dark matter. Though nearly invisible, it may hold most of the galaxy's mass. Its stars are spread thin, orbiting in long, slow arcs. The halo also preserves remnants of ancient mergers, streams and shells of stars torn from smaller galaxies, left like cosmic fossils. It is the galaxy's outer memory, quiet and dim, still shaping what the Milky Way becomes. It contains over 150 globular clusters. Globular clusters are among the oldest objects in the galaxy, tight spheres of hundreds of thousands of stars. They orbit the galactic center in the halo like moths circling a flame. Some are over 12 billion years old, with stars that predate the Milky Way itself. Their stars are metal-poor, formed before the universe created many heavy elements. They serve as time capsules, holding clues to the galaxy's formation. These quiet golden spheres drift above and below the galactic plane, glowing in the dark. Star formation is slowing down. Long ago, the Milky Way was more active, bursting with new stars. But in recent epochs, the pace has slowed. Gas is now spread thin, heated, or locked in forms resistant to collapse. Star formation peaked billions of years ago and has been declining since. This doesn't mean the end, only that we live in a quieter chapter. a mature spiral glowing gently in its middle age, still forming stars, but no longer in a hurry. Some stars formed before the Milky Way had a disk. The disk formed gradually, but some stars are older than it. These ancient stars reside in the halo or thick disk, forming when the galaxy was still assembling, a loose cloud slowly collapsing. By studying them, astronomers peer back into the era before spirals. These stars are the galaxy's elders, silent witnesses to its birth and the long shaping of home. A galactic year is about 225 to 250 million Earth years. As the Sun orbits, it completes one revolution every few hundred million years, a galactic year, a vast cycle dwarfing our calendars. In that time, continents drift, species rise and fall, and epochs unfold. We're currently about halfway through one orbit. The last time we were here, Pangaea was breaking apart, and dinosaurs had not yet emerged. A galactic year is the slow heartbeat of cosmic time. The Sun has completed fewer than 25 galactic orbits. In 4.6 billion years, the Sun has circled the galaxy only around 20 times. Though moving at nearly 830,000 kilometers per hour, the galaxy is so vast, each orbit takes eons. We often think of stars as ancient and unmoving, but our solar system is young on a galactic scale, a newcomer among older, more traveled suns. We are part of the galaxy's motion, but still early in its long story.
The Milky Way's rotation defies Newton's predictions. According to Newtonian physics, stars farther from the center should orbit more slowly, but in the Milky Way, outer stars orbit almost as fast as inner ones. The reason, astronomers believe, is dark matter, an invisible mass in a vast halo. Without it, the galaxy wouldn't hold together. With it, the math works. The Milky Way turns like a solid wheel, not because we understand it fully, but because something unseen holds it in place. The galaxy has enormous molecular clouds. Scattered throughout are vast, dark clouds of cold gas, the raw material of stars. These molecular clouds, mostly hydrogen and dust, can span hundreds of light years. Within their dense interiors, gravity gathers material into new stars and planets. Some clouds are so large and cold, they absorb visible light, appearing as black patches against the sky. They are the galaxy's wombs, hidden places where the future begins in silence. Supernovae stir the galaxy like storms. When massive stars explode, they outshine entire galaxies briefly. These explosions don't just end lives, they create. Shockwaves compress nearby clouds, triggering new star formation. They enrich space with heavy elements like iron and gold, forged in the dying star's heart. Supernovae act like storms in the galactic ecosystem, stirring, fertilizing, and reshaping everything. They are moments of chaos, destructive, radiant, and necessary. Dust hides vast regions of star formation. Interstellar dust, microscopic grains of carbon and silicate, weaves through the galaxy. In visible light, it obscures stars and nebulae, but behind this veil, star formation continues. Infrared telescopes reveal glittering nurseries filled with newborn suns. What looks like darkness is often a cradle. The dust, though it hides, is part of the process, helping gas cool and shielding stellar birth. What seems empty is often the beginning of something bright. There are starless gas clouds drifting through the galaxy. Not every cloud becomes a star. Some are too diffuse or stabilized by magnetic fields. These starless clouds float like silent possibilities, rich in hydrogen but untouched by fusion. They may one day ignite or drift until torn apart. Their gas may be recycled elsewhere. In these clouds, the galaxy holds its breath, waiting for the right nudge to spark something new. The Milky Way recycles matter across generations. Stars live, burn, and die, returning material to the galaxy. Supernovae spread heavy elements, red giants shed layers, planetary nebulae drift outward. This enriched material joins the interstellar medium, cooling and condensing into new stars, planets, and life. Every atom in your body has passed through this cycle, born in a star, scattered into space, gathered anew. The galaxy is not a static stage, but an engine of renewal, making, unmaking, and beginning again. Metal-poor stars hold clues to the early universe. In astronomy, metals are elements heavier than helium. The earliest stars had almost none, forming before earlier generations forged them. Today, astronomers seek metal-poor stars in the halo. These faint, ancient stars preserve chemical conditions from just after the Big Bang, before galaxies matured. By analyzing them, we peer into the primordial past. They are fossils made of light. Some stars wander far from where they were born. A star's birthplace doesn't define its destiny. Many drift away, pushed by gravitational interactions or spiral arms. Some are ejected at high speeds, others migrate gradually. Even our sun is not where it began. Tracing stellar paths reveal a Milky Way alive with movement, exchange, and quiet dislocation. Home for a star may only be
temporary. The galaxy's habitable zone may span tens of thousands of light years. Just as Earth orbits in a Goldilocks zone around the Sun, the Milky Way may have its own galactic habitable zone, a band between the dangerous inner core and metal-poor outer edges. Here, conditions are stable, star density moderate, and elements like carbon and iron abundant. Earth lies within this zone, one quiet orbit in a vast swirl where life might find a foothold. The spiral arms are not fixed structures, they are patterns, density waves rippling through the disk, compressing gas and triggering new stars as they pass. Stars drift into these arms, shine, and drift out. The spiral structure moves at a different speed than the stars, like a traffic jam on a highway. From afar, it looks like order. From within, it's shifting motion held by gravity and time, never still, always flowing. The Milky Way hums with cosmic radiation. Beyond visible light, the galaxy glows with mysterious energy. Cosmic rays stream through space. X-rays and gamma rays shimmer from dying stars and black holes. Radio waves drift from gas clouds and pulsars. These invisible hums reveal what light cannot: the violence, magnetism, and ancient fires within the galaxy's bones. When you look at the night sky, you see only a narrow band of its true spectrum. Beneath the stars, the galaxy hums a hidden symphony. There's a giant gamma-ray bubble above and below the core. Stretching tens of thousands of light years from the galactic center are two vast lobes of high-energy light, the Fermi bubbles. Discovered recently, they glow in gamma rays like twin balloons. No one is sure what caused them, perhaps an outburst from the central black hole or fierce past star formation. These enormous structures drift silently over the galaxy, invisible to human eyes. They are echoes of violence wrapped in radiance. We live in a minor spur between major arms. Our solar system lies in the Orion spur, a quiet lane between the larger Sagittarius and Perseus arms. It's not especially dense or active, which may be why we're here. In this calm between galactic highways, massive supernovae are rarer, radiation storms less frequent. This quiet corner may have given life on Earth time to emerge and evolve. From the outskirts, the galaxy seems dramatic, but here we found enough peace for complexity to unfold. The Milky Way has a bar-shaped center. In infrared light, the galactic core shows a thick, elongated bar of stars, a glowing bridge. This bar rotates slowly, shaping the inner spiral arms. Bars are common in spiral galaxies, forming when stars drift inward and pile along a central axis. Over time, it becomes a dynamic engine, stirring gas, triggering stars, and feeding material toward the central black hole. It's not just a shape, but a sculptor of the galaxy's heart. It's part of a larger structure called the local group. The Milky Way belongs to a collection of over 50 galaxies, the local group. The two largest are the Milky Way and Andromeda, each with satellite galaxies. Scattered around are dwarfs, faint ellipticals, and dark matter-rich galaxies. The local group spans over 10 million light-years, bound by gravity. We're part of this family, quiet, widely spaced, but linked by shared motion. Galaxies in the local group are gravitationally bound. Despite vast separations, they're not drifting apart. Many move slowly toward one another, caught in a slow-motion ballet. Some small galaxies orbit the Milky Way like moons. Others drift independently, but remain tethered. Over time, this group may condense. Galaxies may merge or be absorbed. It's not static, but a gentle gathering of cosmic islands drawn closer by time and gravity. The galaxy's disk has a thick and thin component. The Milky Way's disk is layered. The thin disk, where we live, is dense with young stars and gas. Above and below lies the thick disk, older, puffier, more diffuse. Its stars are older, with fewer heavy elements, moving in tilted orbits. They likely formed under different conditions or were stirred by early collisions. The disk is textured, layered, and shaped by time, like sediment in a cosmic ocean. The galaxy's magnetic field threads through the disk. Though invisible, a vast magnetic field weaves through the Milky Way, shaping cosmic rays, gas collapse, and matter flow. It aligns with spiral arms, forms arcs, and twists into loops. Studying it requires radio telescopes, but its presence is unmistakable. The galaxy doesn't just glow with light, it breathes with magnetism, a subtle pulse running through its bones. The interstellar medium is full of invisible structures. Between stars lies more than emptiness. A thin blend of gas, dust, and plasma weaves like a fog. To the naked eye, it's mostly invisible, but radio and infrared telescopes reveal filaments, bubbles, shock waves, and cold clouds where stars are born. Supernovae carve cavities, stellar winds sculpt shapes. The space between stars is not a void, but a shifting web of matter and magnetism, the quiet fabric from which galaxies evolve and life begins. Cosmic rays constantly pass through us from the galaxy. Every second, high-energy particles stream through your body, launched by exploding stars. These cosmic rays travel near light speed, bending through magnetic fields and colliding with Earth's atmosphere. They carry stories from across the galaxy, evidence of ancient supernovae, traces of distant acceleration. Even as you rest, the galaxy whispers in particles, in silence, in lightless rays. The galaxy is not symmetrical. Though often shown as a neat spiral, the Milky Way is unbalanced. One side of the disk is thicker, spiral arms vary in brightness, the warp is lopsided. These asymmetries may stem from gravitational encounters, past mergers, or dark matter. They remind us that galaxies, like living things, carry traces of their histories, scars of collisions, wrinkles of time, quirks of uneven growth that give character and depth.
The oldest known star may live in our halo. Drifting high above the galactic plane is a star nearly as old as the universe. It contains almost no heavy elements, a signature of formation soon after the Big Bang. It likely formed over 13 billion years ago, long before the Milky Way took shape. Burning quietly with a soft red glow, it is not just a star, but a time capsule, a living relic from the universe's earliest dawn. The center of the galaxy spins faster than the outskirts. Near the core, stars orbit rapidly, pulled by strong gravity from stars, dust, and the central black hole. They complete revolutions in just millions of years. Out in the suburbs, like where our sun lives, stars orbit more slowly, taking hundreds of millions of years. This uneven rotation creates twisting patterns, stretches spiral arms, and keeps the disk from behaving as a solid structure. The galaxy moves like a great wheel whose rim lags behind its core. Spiral arms are shaped by density waves. They are not fixed trails, but patterns formed by waves of higher density moving through the disk. As gas and dust pass through, they compress, triggering star formation and lighting the arms with bright young stars. These stars eventually drift out while new ones form, creating a self-sustaining illusion of structure. Like ripples in a pond, the arms are dynamic, always in motion. From afar, they appear still. From within, they are a dance of matter and rhythm. Stars are born from cold, collapsing gas. In dark galactic arms, star formation begins in silence. Massive molecular hydrogen clouds, chilled near absolute zero, drift through space. Within them, gravity takes hold. Dense regions collapse under their own weight, heating and spinning until nuclear fusion ignites a new star. From the coldest shadows come the brightest lights, spun gently into being by gravity's quiet force. Star clusters can dissolve into the galactic field. Many stars are born in groups, tight clusters from the same gas cloud. Bound by gravity, they drift together for millions or billions of years, but tidal forces from the galaxy, close encounters, and internal dynamics pull them apart. Stars peel away until the cluster fades into the general star field. Even our Sun was likely born in a cluster. Its siblings are now scattered, dimmed, or lost in distant haze. The galaxy contains ancient hypermetal-poor stars. Among the rarest objects are hypermetal-poor stars, with atmospheres containing almost no elements heavier than helium. Some have less than 100,000th the iron in the Sun. They are believed to be among the first born after the earliest supernovae, incredibly old and pure, scattered in the halo like lanterns from the dawn of time. Each is a relic, a glowing signature from a near-forgotten epoch. Planetary systems form throughout the galaxy. Planets are a natural consequence of star formation. As a new star ignites, a rotating disk of leftover gas and dust surrounds it, clumping into worlds. Across the galaxy, planetary systems are common, some with gas giants, others with rocky planets. Some may resemble ours, others defy expectations. The galaxy isn't just full of stars, it's full of solar families, each with unique balance, orbit, and potential. Earth is near the co-rotation radius. In the Milky Way, spiral arms rotate at a different speed than stars. But there's a special distance, the co-rotation radius, where stellar speed matches the arm's rotation. Our Sun orbits near this boundary. This match may help us avoid frequent spiral arm crossings, places with higher star density, more supernovae, and disturbances. We live in a stable neighborhood, shielded not by walls, but by resonance. The Sun bobs up and down through the galactic plane. As it orbits, the Sun doesn't follow a flat path. It drifts above and below the plane like a cork in slow motion, rising and falling over tens of millions of years, a vertical oscillation from the galaxy's gravitational tug. Some wonder if this motion influences extinction cycles on Earth, though evidence is unclear. Still, it's a reminder. Even on a steady path, the Sun sways softly through space. We don't know what dark matter is, but we know it's there. Dark matter makes up most of the galaxy's mass, yet never seen directly. It doesn't emit or absorb light, it passes through ordinary matter. But its gravitational effects are unmistakable, holding the galaxy together, explaining stellar speeds, shaping cosmic structures. Without it, the Milky Way would fly apart. Astronomers detect it by watching how it moves other things. It's the hidden scaffolding, invisible, and still a great mystery. There's more mass outside the disk than inside. Most visible stars lie in the disk, but most mass resides elsewhere, in an enormous dark matter halo extending far beyond the furthest stars. This halo outweighs the disk greatly. It holds ancient stars and globular clusters sparsely, but its true bulk is unseen. When we picture the Milky Way, we see its glowing surface, but the mass defining it, its gravity, motion, reach, is mostly hidden, enveloping everything like a quiet shroud. The Milky Way's core may have flared as a quasar. Today, the galactic heart seems quiet, but evidence suggests it once was dramatically active. Huge gamma-ray structures like the Fermi bubbles and traces of high-energy light hint that the central black hole may have once flared as a quasar, a brilliant beacon fueled by infalling matter. Quasars are among the universe's brightest objects.
If the Milky Way once burned like this, it would have looked dramatically different, a spiral wrapped around a blinding heart. That time has passed, but echoes remain. The galaxy's structure changes over billions of years. Galaxies evolve. Spiral arms shift, bars form and dissolve, gas flows inward and outward. Stars are born and die, changing the population. The disk's shape, warped, rippling, lopsided, slowly alters. Encounters with dwarf galaxies and dark matter bend or twist it. Over eons, the galaxy's silhouette shifts like a drifting cloud. The Milky Way of today is not the one that was, nor the one that will be. Its beauty lies not in permanence, but in quiet transformation. Gravitational waves ripple through the galaxy from distant mergers. Across the universe, massive objects collide. Black holes spiral together, neutron stars crash, galaxies merge. These events send gravitational waves, ripples in space-time. Though faint, some pass through the Milky Way, distorting space slightly. Observatories like LIGO and Virgo have captured several. New experiments aim to detect the cosmic background hum of these waves. Even now, as you rest, space itself shifts, not enough to feel, but enough to tell us the universe is changing. Some stars orbit in elongated, tilted paths. Not all stars move in neat circles. Some follow stretched ellipses, looping high above and far below the disk, tilted at odd angles. They likely come from different origins, relics of swallowed dwarf galaxies or survivors of ancient upheavals. Their orbits are clues, 3D maps of the galaxy's chaotic past. By tracing their motion, astronomers reconstruct the invisible architecture of the Milky Way's mass and memory. These stars drift like messengers from disrupted systems.
The Milky Way emits neutrinos we can barely detect. Every second, trillions of neutrinos pass through your body, from the sun, supernovae, cosmic rays. The galaxy is bathed in them, yet they are so light and unreactive, they slip through almost everything. Special observatories buried underground try to catch a few, flashes from rare collisions. Neutrinos carry information from places we cannot see: stellar cores, collapsing giants, the galaxy's unseen energy. They are whispers of cosmic fire. Interstellar space isn't empty, it's a turbulent sea. Between stars, space is not smooth. The interstellar medium is stirred by shock waves, magnetic fields, and stellar motion. Temperature varies wildly. Material flows collide, mix, fragment. Clouds stretch, fold, tumble. This creates slow-motion turbulence like an ocean swirling through the disk. Star formation and galactic evolution are affected by this restless sea. What looks like calm starlight is, up close, a dynamic, rippling fabric. The galactic halo may contain rogue planets. Planets aren't always tethered to stars. Some form and are later ejected, others never had a star. These rogue planets drift cold, dark, and alone. Though hard to detect, studies suggest billions may exist in the Milky Way, some in the outer halo. Without light or warmth, they float unseen, warmed only by internal heat. Orphans of the galaxy, planetary drifters on lonely paths through darkness. Magnetic fields shape the flow of cosmic dust. Interstellar dust, tiny grains of carbon and silicate, moves not just under gravity, but under the galaxy's magnetic field. These fields thread like invisible currents, guiding charged particles and influencing gas and dust alignment. In some regions, dust grains spin, emitting faint microwave light. In others, they align, polarizing starlight. Understanding this helps trace magnetic structure. Dust isn't passive, it dances to a magnetic rhythm, tracing hidden patterns. Some stars are enriched by neutron-star collisions. When two neutron stars spiral together and collide, they create a kilonova, a violent explosion, forging heavy elements like gold, platinum, uranium. These materials are cast into space, mixing with gas and forming new stars. Some Milky Way stars carry chemical fingerprints of these rare events, enriched in elements only from such collisions. They are not just luminous bodies, but record keepers of ancient cataclysms, burning with stellar wreckage. The Milky Way may have a hidden bar within a bar. At the galaxy's heart lies a bar of stars, but deep within, hints suggest a smaller, tilted bar rotating independently. Obscured by dust and distance, its gravitational influence appears in nearby star and gas motion. Such inner bars may help funnel material toward the supermassive black hole, feeding it and shaping core dynamics. The center isn't one simple shape, it's a layered labyrinth of light and motion. Gas inflows feed the galaxy from the cosmic web. The Milky Way isn't closed. It draws fresh gas from intergalactic space, long, tenuous streams flowing through the cosmic web. These inflows provide raw material for new stars, replenishing losses. Some gas arrives as cold filaments, slipping quietly in. Others fall hotter, shock-heated, lighting up in UV or X-rays. These invisible rivers sustain growth, linking the galaxy to the larger universe. Even now, the Milky Way drinks from distant reservoirs. Hot gas bubbles form chimneys out of the disk. When massive star clusters go supernova, they create enormous cavities, super bubbles of hot gas punching upward through the disk, venting into the halo. These chimneys regulate interstellar pressure, redistribute metals, and shape halo structure. The galaxy breathes not just within the disk, but through towering columns carrying energy up and out into the dark. The galaxy shines in X-rays from old stars and black holes. Though calm in visible light, the Milky Way glows fiercely in X-rays from its core, collapsed stars, black hole edges. White dwarfs and neutron stars in binary systems siphon matter, heating it to millions of degrees. Hot halo gas emits faint X-rays, revealing the galaxy's larger skeleton. Telescopes like Chandra paint a different portrait, not a tranquil spiral, but a realm of extreme temperatures, compact remnants, and hidden radiation.
Pulsars act as cosmic clocks throughout the Milky Way. When massive stars collapse into neutron stars, some spin fast with sweeping radiation beams, pulsars. Some pulse hundreds of times per second, regular and measurable. Astronomers use them as timekeepers, tracking signals to measure distances, test gravity, search for gravitational waves. Across the galaxy, pulsars blink quietly, remnants of death, but beacons of order, keeping time for epochs, ticking steadily in stellar silence. Radio waves map the hidden structure of the galaxy. Much of the Milky Way is invisible in visible light, but radio waves slip through barriers, revealing cold hydrogen gas, magnetic fields, pulsars, supernova remnants, distant quasars. Using radio telescopes, astronomers have mapped spiral arms, measured the disk's warp, discovered star-forming regions cloaked in darkness. Where light is blocked, radio soundings let us see. The galaxy speaks in a language we can't hear, translated into shape and shadow. The Sun was likely born in a stellar cluster. Stars rarely form alone, they're usually born in groups from the same gas cloud. Our Sun was almost certainly one of these, sharing space with hundreds or thousands of siblings. Over time, gravitational tides, passing stars, and galactic motion scattered the cluster. Most siblings have wandered far, flung into different orbits. Some may still shine nearby, invisible among stars, lost family in a sea of light. The Sun's siblings are scattered across the galaxy. Though the birth cluster dissolved, astronomers search for lost siblings, stars sharing the Sun's age, motion, and chemistry. Using surveys like Gaia, researchers hope to identify them. A few candidates have emerged, stars that may have shared our origin. If found, they could reveal details about the Sun's early conditions. Our place isn't entirely solitary. Somewhere, the Sun's ancient kin may still shine. The galactic disk wobbles as it spins. The Milky Way's disk isn't perfectly flat. It wobbles gently, rippling like a spinning plate off balance. The wobble is most visible in outer regions where the disk bends up on one side, down on the other. It may be caused by nearby dwarf galaxies, dark matter interactions, or internal asymmetries. The wobble rotates slowly like a vast wave through stars. From Earth, we don't feel it, but from afar, the galaxy is a breathing, undulating sheet. Galactic tides can distort star clusters and streams. The Milky Way's mass exerts tidal forces on everything within it. Star clusters, satellite galaxies, and globular groups feel this uneven pull. Over time, tides stretch and distort them, drawing out stellar streams or peeling stars away. Many faint arcs across the sky are remnants of such encounters, clusters being unraveled, galaxies slowly torn apart. The galaxy doesn't break them suddenly, it unravels them patiently over millions of years. The galactic mass is still uncertain. You'd think we'd know our galaxy's mass, but measuring it is difficult. Stars and gas make up only a small portion. The rest is dark matter. Estimates vary, some near 1 trillion solar masses, others higher. Uncertainty comes from measuring distant stellar speeds, limited by data and invisible matter. The Milky Way is our home, but its weight remains a quiet mystery. It may be heavier than Andromeda. Astronomers long assumed Andromeda was more massive, but recent measurements suggest the Milky Way's dark matter halo may be broader and denser. If true, our galaxy could outweigh Andromeda, despite a modest appearance. This matters for predictions. When they merge, their relative masses will shape the encounter. The Milky Way may look gentle, but beneath its spiral arms, it carries more weight than once imagined. The Magellanic Clouds may be on their first orbit. The large and small Magellanic Clouds, bright satellite galaxies, may be newcomers. Their motion hints this could be their first close pass, not long-standing companions, but wanderers just falling under the Milky Way's pull. Their arrival has stirred the outer disk and warped the galaxy's shape, as if responding to a new gravitational guest. The quiet sky is full of first encounters. The Magellanic Stream is a ribbon of stripped gas. Trailing behind the Magellanic Clouds is a vast ribbon of hydrogen gas, the Magellanic Stream, stretching hundreds of thousands of light-years across the southern sky. Pulled away by tidal